Fold a single piece of paper in half 42 times, and it becomes thick enough to reach the moon. Nobody believes that the first time they hear it. And that exact same mental blind spot, the one that makes this sound impossible, is the same one that's made humanity chronically blindsided by pandemics, AI progress, and debt. We're not bad at math. We're bad at exponential math specifically, and that gap is starting to get dangerous. Let's actually do the paper fold, because the math is the whole point. A regular sheet of paper is about 1/10 of a millimeter thick. Fold it once, it's 2 sheets thick. Fold it again, for sheets. Every fold doubles the previous thickness. After 10 folds, you've got about 100 sheets stacked up, roughly the thickness of a textbook. Completely unremarkable. Your brain looks at that and assumes the growth is basically over. Here's where the intuition completely breaks. By fold 30, that stack is already over 100 kilometers thick, taller than the edge of space. By fold 42, doubling that same number one more time, the thickness has surpassed roughly 384,000 kilometers, the average distance from the Earth to the Moon. 42 folds. Not 42,000. 42. Almost everyone's gut reaction to this fact is disbelief. And that gut reaction is the entire subject of this video. There's a well-documented pattern in cognitive science called exponential growth bias, a consistent, measurable tendency for people to underestimate how fast exponential quantities grow, even highly educated people, even professionals who work with numbers for a living. Researchers studying this bias have found that when people are asked to estimate values that grow exponentially, like compound interest on a loan or savings account, they systematically guess numbers far too low, treating the growth as if it were closer to a straight line. Your brain isn't malfunctioning when this happens. It's using the tool it evolved with. Almost everything in the ancestral environment that mattered for survival grows linearly or stays roughly constant: how far you can walk in a day, how much food a hunt yields, how fast a predator can close a gap. Exponential growth, where each step doesn't just add to the previous one but multiplies it, essentially never showed up in a form our brains needed to track. So we never built good intuition for it. We built excellent intuition for addition, and mediocre to terrible intuition for repeated doubling. That gap between how exponential things actually behave and how we instinctively expect them to behave isn't just a fun paper folding trivia fact. It's cost real lives, more than once, in ways you can point to directly. Case 1. The early days of COVID-19. In January and February of 2020, case counts in many countries looked small, tens, then hundreds. To a brain wired for linear thinking, small numbers feel safe, and slow-looking growth feels like it'll stay slow. But an infection spreading exponentially can look almost unremarkable for weeks, right up until it suddenly doesn't. Case counts that seem to be crawling upward can, after enough doubling periods, explode past hospital capacity in a matter of days. Public health responses in numerous countries were criticized afterward for reacting to the outbreak roughly a doubling period or two later than the exponential math actually demanded, a delay that, compounding across an exponential curve, translated into dramatically higher case and death totals than an earlier response would have produced. Case 2. AI capability growth. Public perception of AI systems has, over and over, been anchored to how the technology looked a year or two earlier, treating slow-seeming early progress as evidence that dramatic capability jumps were still far off. Then a new model arrives that can suddenly do things that seemed years away, and the reaction is shock, even though the underlying trend, when you actually plot compute and capability over time, had been on a clearly exponential trajectory the entire time. The surprise isn't really about the AI. It's about our default assumption that progress continues in a straight line until proven otherwise. Case 3. Debt and compound interest. A debt growing at a seemingly modest interest rate doesn't grow by the same amount every year, it grows by a percentage of an already larger balance, which means the absolute increase gets bigger every single cycle. National debt crises and personal debt spirals both follow this same signature: years of manageable-looking numbers, then a rapid, seemingly sudden collapse that was, mathematically, entirely predictable from the start, if anyone had been tracking the actual growth rate instead of the current-looking number. In every one of these cases, the raw information needed to see the danger coming existed well in advance. The failure wasn't a lack of data. It was a failure of intuition about what that data implied. So what does actually thinking in exponential terms look like in practice? The key mental shift is this: stop asking how big is it right now, and start asking how long does it take to double, and how many doublings are left before this becomes a serious problem. A quantity doubling every 3 days looks tiny at day 1. By day 30, that's 10 doubling periods, a 1,000-fold increase, even though nothing about the daily experience of watching it felt dramatic along the way. There's a genuinely useful mental shortcut for this, sometimes called the rule of 70. Divide 70 by the percentage growth rate, and you get a rough estimate of how many time periods it takes to double. A quantity growing 7% per period doubles in roughly 10 periods. Suddenly, a boring-sounding annual growth rate translates into a concrete, checkable prediction, instead of an abstract percentage your brain has no intuition for. None of this requires being a mathematician. It requires building one specific habit your brain didn't evolve with by default. The paper fold isn't really a trick question. It's a demonstration of exactly where human intuition quietly runs out, right at the moment it matters most. Pandemics, AI capability, debt, all of these are ordinary exponential curves, and every single one of them looked manageable and still early right up until the point where the math had already decided otherwise. The fix isn't becoming smarter. It's remembering, deliberately, every time you see something growing slowly, to ask how many doublings are actually left before slow stops being the right word for it. If this is the kind of thing that changes how you look at the next headline about AI progress or case counts, share it with someone who needs to see it. This is genuinely one of those ideas that matters more the earlier you catch it. Subscribe for more of these deep dives into how our own thinking quietly fails us. And tell me in the comments, where do you think exponential growth is being underestimated right now?